All right. Good morning and welcome all. So we are edging our way towards transformers, the technology at the heart of large language models. And so even 2 years since the birth of GPT, or the release to the public at large, I'm still amazed by its capabilities. And yeah, probably like most of you, I use it a lot. Just curious, to whom does it feel intelligent when you interact with it? Okay, so I'm not saying it is intelligent because on the one hand, I like to think it's not, and also sometimes, you know, I stumble across really weird mistakes. But I mean, as humans, you know, generally we have to solve an ill-posed problem when we deal with the world. By that, I mean, if we take vision as an example, so, you know, strictly speaking, you know, these benches are opaque, so I cannot see through these benches. And in principle, behind any of the benches hidden out of sight, you know, there could be, I don't know, a monster lurking, or there could be a hole going right through the middle of the earth, or, you know, something of that kind. But I believe it's not, well, both because I've been in this hall before, but even if I was here for the first time, I would have assumptions about, you know, what's behind, or what's behind the parts that I cannot see. So when we navigate in the world, actually our sensory input is limited. So it's too limited to strictly, you know, infer with good confidence what is going on around us. But we have a strong world model coming partly. I think partly it's ingrained, so evolution produced it, and then partly it's you know, our experience of navigating this planet for years and years. And so our addressing this ill-posed problem goes by means of simplification, or, you know, we make simplifying assumptions. We tend to use, in most cases, the simplest explanation that, well, matches the phenomena we observe. And now coming back after this detour to this question of intelligence or not, it's just when we deal with these systems by now, for many people, it is the simplest description or assumption to just say, you know, it behaves as if it were intelligent. You know, maybe it isn't, but it sure feels like it is. And the argument for people who think that it's not, the argument becomes harder and harder to make. So a few years ago, until 2 years ago, basically, the Turing test was widely considered as a viable measure for intelligence. The Turing test being that if we, through a chat terminal, so just we have a keyboard and a screen, and if we chat with the system, can we determine whether on the other side there's a woman or man, versus is there on the other side a machine? And these systems, at least if they're not fine-tuned to be, you know, politically correct and always say, nah, I'm just a machine, yada, yada, these systems now pass the Turing test. So if we still believe that it's not intelligent, we have to move the goalpost of what is our definition of intelligence. And yeah, this is an interesting outlook, because so right now the system can only trick us into believing it is a human if it wants to, if we have this sort of keyboard and text interface. but it is more and more coming into the realm of the feasible to have a real-time synthesis of an avatar on the other side, and then you will have a video conference, and you're wondering, is it truly a person on the other side? And that can have all kinds of innocent uses, like you can send your avatar into boring meetings, but it of course opens all possibilities for all kinds of abuse. And yeah, I'm already wondering, sort of, how will I deal with the situation in a few years when I'm in a video conference and I'm wondering, did the person come himself, or did they send their avatar? And how am I going to find out? And sometimes it's not so obvious, even now, when people, just, all right. Maybe implausibly, this explosion of intelligence, or the thing that currently comes closest to this artificial general intelligence, has large language models at their heart, and large language models use transformers, and transformers use attention. And now we slowly come to today's lecture, and the transformers themselves. I was already advertised. That will be a guest lecture by Leticia Pachelabescu, who I looked it up. It's only 8 years since she wrote her bachelor thesis in my lab, and now she's an expert developing large language models with this Aleph Alpha company, which is not far from here. So she will give the lecture next Tuesday. And so where did this idea for attention come from? And I would like to start with word embeddings. And just like the computer vision community had their aha moment when AlexNet came along, so did the community of linguistics or computer linguistics, because, before the advent of computer linguistics, the processing of natural language, either typed or also spoken, that was the domain of linguistics. And that was a bit of how should I say, the community to the outside appeared a bit hermetic, because if I read a philosophical essay, which I don't often, but at least I understand the words. I might not understand the meaning, but I understand the words. And if you read an essay from linguistics, I don't even understand the words. Yeah? So they've been very good at creating their own, very erudite, Greek, Latin, etc. terms. And it didn't help them. So there's a famous quote by the head of IBM speech recognition from the late 80s, who is quoted as saying, and it's supposedly true, that every time I fire a linguist, my recognition rate goes up 5%. And that was at the time when engineers started to take over, and when linguistics was replaced by computer linguistics. And to a linguist, a word is a construct and all kinds of things. To a computer linguist, a word is just a point in 4096 dimensional space. Yeah, and in 2013 specifically, this method word2vec was published, and then famous diagrams were made, such as these. So I cannot draw 4096 dimensions, but I can plot 2, and you can have a coordinate for man, and you can have a coordinate for woman. And then if you add, and then there is a coordinate for king and a coordinate for queen, and this really worked. Yeah. So if you took this difference vector and you added that difference vector to woman, then you did not end up precisely at queen, but you ended up at one of a set of nearby terms, which could include princess or so. And then people made analysis of, was queen the first hit or the third hit, or how close was it? How many nearest neighbor was it? And in the OneNote document that you have, there are more pictures or diagrams like this, and these coordinates, they are not invented. Yeah, so I did not find again the address of the blog, but somewhere there was really Python code, and all these different vectors were computed and then plotted in this kind of space. And now this was astounding and really a step forward for the community. But there are also, as an extreme example, there are homonyms, so one of the words that linguists like. Those are words that are written in the same way, they are pronounced in the same way, but they have different meanings. Yeah. So, for example, we might have the club. The club could, on the one hand, be the golf club. So it's the thing you use to, to hit your golf ball, if you're into this. And there is also the club that you might visit on a Saturday night. Yeah. All right. So if I write golf club or if I write nightclub, it's clear that those are different coordinates. But if I just say club, and I use something like word2vec, well, it's presumably somewhere, not necessarily now on this, not necessarily on the line segment, but somewhere in between will be just the word club. And now, for all kinds of applications, but specifically if you want to use something like a large language model, it is good to better understand what club are we talking about here. And if we now have a sentence such as, let's say, she visited the club, then we could, of course, find the coordinates of all these words in the space. And then, I don't know, we could take the coordinate club and add maybe, let's say 10% of each of these vectors, for example. That would be, one way forward, because if she visited the club, or if she swung the club, or let's make it a he here. He swung the club. If we add 10% of the coordinates of those words, maybe this will nudge us in an informative direction. But if this was a she or a he who swung the club, or if it was a he or a she who visited the club, that doesn't really. So here, male or female does not inform us on the nature of the club. But visited versus swung does inform. The is completely uninformative. It's all over the place. Yeah, and in English you have always, a the somewhere. So it makes sense, if we want to update our coordinates in such a word embedding representation, it makes sense to concentrate or focus or attend to some of the neighbors more than to others. Yeah, so, for example, here, visited would be informative, or here, swung would be much more informative than the she or the he. Okay, and this is something that attention can give you. And I want to introduce attention as a mechanism to produce a set of features, or no, to produce a feature vector given a set of inputs. And you see, one approach would be to say, all right, I'm deciding which is the most informative word. The single most informative word could be visited versus swung. Yeah? But you know, the sentence might be longer. She visited the club perhaps on Saturday night. All right, visited is informative, but maybe Saturday night is also more associated with visiting a club rather than golfing, which most people prefer to do when it's not dark outside. So we might want to use here also the night. And now we come to a new kind of problem that we've not seen before, because previously, you know, when we had, you know, an MLP, an encoder, you know, anything, we always had some function. We were, you know, we've been discussing linear methods, we've been discussing nonlinear methods, but we always had a function of some input, and then it had parameters, and this was our output. And, you know, let's say the input here, we've always said that it's p-dimensional, supposed to write larger. The input was p-dimensional, and, you know, perhaps our output, in our case, we take maybe here a 4096 dimensional vector, a word embedding, and we want to produce a new word embedding. So our output here should have the same dimensionality as the input. And one way we've seen how to do that would be using a multi-layer perceptron. But we always had an input of a fixed dimensionality. You know, we could also say that, for example, in so-called Siamese networks, maybe we would have a network that accepts two inputs. Now we could have some procedure that decides which is the most informative word, and then we add that other most informative vector as input, and we could, for example, concatenate those two. But also in this case, the input dimensionality is always fixed. Yeah? So here the input is 2p times 1 dimensional. And here we have something qualitatively new. If we want to take potentially all words into account, we just want to weigh them, you know, differently. Namely that we want to produce an output given a set of inputs. And we don't know in advance how many members this set has. So our aim here is to make some prediction. And in the specific case of attention, we can say the prediction should be just an update to the original feature vector of one of the items. Given a set of inputs. And the difficulties or the challenges are that the set can be of varying size. So it has sometimes more members and sometimes fewer members, larger or smaller cardinality. And this size is unknown in advance. And Well, the problem that we want to address is that a single item or a single member of the set, I'm writing here, and it's not a very technical term, is not so informative. Yeah, so somehow the information is in the set more than in any single item. Okay, and you know, if you now go through your head the kind of techniques that we've seen in this lecture, we always had some trick to come to a fixed dimensionality. Yeah, so when we were discussing convolutional neural networks, the convolution itself does not care how big the image is, but later on, when it comes to image classification, there's always some max pooling stage and so on, and in the end we come to a vector of fixed dimensionality. And in computer vision specifically, the trick was, okay, if our image is not of dimensions 224 by 224, then we rescale it and make it 224 by 224. But you know, if you have a sentence, you know, how do you make the sentence, how do you make any sentence 5 words long? You can, of course, you know, you can omit other words, or you can, you know, omit maybe the most frequent, the least informative words. But this is a qualitatively new problem, yeah, to make predictions given a set of inputs. And this is now where attention comes into play. And I've here already used, you know, these words to focus on or to attend to. And this is one out of 2 contributions that this famous paper made, Attention is All You Need, from 2017. It has been a very impactful paper, so 150,000 citations to date. And it also unfortunately spurred a race of publishing papers that are variations on this title. Attention is not all you need, attention is all you need for vision, attention is not nearly, blah, 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 blah. Yeah, I mean, the bar for humor in machine learning is really low, but those titles, you know, they didn't clear the bar. I was really happy when, you know, after 5 years or so, it subsided a little bit, yeah? The fashion, you know, if you write a paper, you know, please don't make a pun on attention is all you need, okay? All right, good. So, as always, okay, I'm going to write more words here, so I'm starting with attention there. As always, we collect our samples in a matrix which is P by N. So here we have N items, each are P dimensional, and these could, for example, be these columns here could correspond to single words, and the dimensions would correspond to the 4096 numbers that something like word2vec gives to me. And so this paper made 2 important contributions. The Attention is All You Need paper, the one was the scale dot product attention, and the other one was the transformer itself. And here we start with attention. And they use terms that were derived from the information retrieval community, namely query, key, and value. And query in words, I would say that's the, you know, don't quote me on this, yeah? But I'm calling this the question a sample asks. And the key would be how well a sample responds to a question. value, as the name implies, would be the value of the sample itself. And there is the possibility here to introduce a bit of an asymmetry. So the query is going to be a new matrix. The key is going to be a new matrix. And the value is going to be a new matrix. And here, this was P by N. And then this matrix here normally would be P by P. And the result would again be P by N. And now, you know, we could use just the identity matrices here. We could use just the original observations. But these matrices have two functions. So on the one hand, they allow us to inject more parameters into the procedure. So they are a means to make the model more expressive. And on the other hand, they allow us to bring an asymmetry into the discussion. The example that Bishop gives is if we have the two words chisel and tool. A chisel is ein Meißel in German. Yeah, it's a very particular tool. So chisel could very strongly respond to tool, but tool might not respond as strongly to chisel because we have all kinds of tools. Yeah, we have text editors, we have hammers, we have chisels, we have you know, all kinds of, we have kitchen knives, we have all kinds of things that you could call tools. So this is also a means to bring an asymmetry into the query versus key. And then the value we could really leave as is, but again, to allow the model to become more expressive, we can multiply this with another matrix of parameters. All right, and now the question is, how do we get an attention out of that? And the proposal has been the following. Scaled dot product attention. So I'm going to write A for attention. And what is pretty clear is that we want a nonlinearity. The softmax, which, as we have discussed, is really a soft argmax. That's important to have the nonlinearity in there. Now, what's the argument of the nonlinearity? That's much more debatable. And dot product is not the only choice at all. Yeah? So one could also take, for example, the sum of the key and the query. Yeah? So the sum was something I insinuated in this example that we could use. I said we have some word embedding vector, and then we can add maybe 10% of that vector. That would be a summation. And but if we have different things or different vectors that we could sum over, maybe we want to, you know, put more weight on some than on others. This putting more weight on some than on others is what the nonlinearity gives you. And what's inside the nonlinearity, there's much more freedom. And in fact, there is also the sum attention mechanism, which is also quite successful, not just the dot product. All right, but in this particular paper, and the one that's most widely used is the dot product. So the key, the matrix of keys is multiplied with the matrix of queries. And that's just normal matrix multiplication here. And we can, look a little bit what that does. So this would be K transpose. This would be a matrix Q. And well, what it gives me, so this is here n by p, and this one is p by n. And what this gives me in terms of the matrix product is how much the first element is characterized by its key, how well this is compatible with the query vectors of all the other examples. And I can do the same for the second element and so on. Now, as we have very many dimensions, so this was here n by p, and this was p by n, and the result here would be n by n. And as we have very many dimensions, some entries might come to completely dominate others. And this is why the authors proposed to scale with the square root of the dimensionality. To make it a bit less extreme. Yeah, so if one entry in the soft argmax completely dominates the others, this will lead to very, very small gradients and make learning harder. All right, so we have now an asymmetric attention matrix A, and this attention we can use to produce updated features. Again, check the dimensions. So my matrix of values would be p by n. The attention matrix would be n by n, and so we get overall something that is p by n. Okay, and please leave a bit of space, and then we can use a layer norm. That's like batch norm, except that the means are taken across layers here, and there's another chance to inject parameters to make the system even more flexible, and there's also a skip link here. And now I have x written on the left and on the right hand side, and so it will seem safer to introduce an index for the layers. So this was the output from the ELF layer, and this is what comes after this attention layer. Yeah, I get an updated version. And now, as in typical neural networks, I can stack layers. So I will have a different weight matrix for each layer. And also this intermediate result here, I can index with the layer, and I can do the same for the value and attention matrices. And yeah, I can nicely decorate all my original equations with an index for the layer here. All right, and let's look once more at what this attention here does. So the first column here would be the query of the first item in my set. There's no ordering amongst these items. It is just, you know, in my enumeration, it's just the first item in the set. And this here I call very informally this is the question asked by the first item. And now this question of the first item is compared with, you know, is evaluated how well all the other samples respond to this question. And so multiplying these two gives me now this new matrix, which is n by n. And here along the first column, I have the information how well did all other items respond to this question. And now I want to somehow normalize this thing, yeah? And so now I can use my soft argmax. So I can apply the nonlinearity, and this nonlinearity will then make sure that all these entries are non-negative and that they sum up to 1. And so this is what we get in the attention matrix. In the first column, so if we now apply the nonlinearity, what this would now tell me is how strongly the first item attends to all others, including itself. And if you now here think about the rules of matrix multiplication, we have a P by N matrix here of values, and we multiply it now from the right with this attention matrix, which has the wrong dimensions here. No, it's correct. Check. And again, this was the dimension across the samples. And so it tells us for the first dimension how strongly I want to weight all the other samples in computing a new representation. And then I do the same for the second feature and so on. Okay. After the break, I will add more indices, but let me ask so far if there are any questions so far. Yes. The question was, how does it relate to input of undefined size? Because in all our operations here, the parameters that I have are these matrices W, and you see that my parameters do not depend on the number of inputs n that I have. Yeah. So here, if we say she visited the club on Saturday night, those would be the columns of this matrix. And if the text goes on, we have more columns. And of course, it changes all these intermediate results. But importantly, my parameter matrices, they are independent of the size of the set. Good question. Yes.
The A matrix is the tension that gives us how well the items respond, but what is that?
Okay. So these are my updated features, and I could stop here, but if I want to add skip links, I have this extra equation here, and I can introduce more parameters. But these are really already my updated, what I have here are the updated features or representations for all the items in the set. And then I can further transform them a little bit and add skip links. Yeah? But really, the important stuff has happened by that time. Yes? Yeah. Yeah. So is there a rationale for this particular kind of thing? So there is another perspective on what do I do when I have a set of items, and what we really want is permutation equivariance. So if I permute the columns of my input matrix X, then I want those columns to be permuted accordingly. And this permutation equivariance is at the heart of graph neural networks, which we will discuss separately in more detail. And as the name implies, in graph neural networks, there is normally a non-trivial graph. Yeah, so we have items and edges, or we have nodes and we have edges, and not every node is connected to every other. And in these graph neural networks, there are three main classes of operations or of messages that other items in the set can send to a particular item, and they are of growing generality. Yeah? So we need some aggregation operator, and one possibility of what other nodes j can send to some particular node I is to just multiply with a number that depends on the identity of the sending node j, but not on the features of that node j. Another possibility is to have messages which depend on both the sending and on the receiving node. This is the most general class, and the attention mechanism is a compromise. In the attention mechanism, we have multipliers that depend on the sending and on the receiving node. But this would be a scalar. So this is 1 times 1, just like here, these coefficients is 1 times 1. And this is then multiplied with some function of the features of the sending node. So this here gives rise to graph convolutional networks, or GCNs. And this here gives rise to message passing neural networks. And these here, this is an intermediate class. These are the graph attention networks. So I would say this one is canonical. We could argue that that one is canonical, and this is, in terms of flexibility, apparently a sweet middle spot. Now, what we have here is a special case of graph neural network, namely, here each item can attend, or each sample can attend to every other. So in other words, we here operate on the complete graph. So we could say that this attention mechanism, it is a graph attention network, but on a completely connected graph, on an uninformative graph. And well, you specifically know from last semester this formula, and we will, at the end of the semester, look at my favorite problem and application, namely a difficult problem from quantum chemistry. And there, one really needs message passing neural networks, but for these natural language processing applications, this has turned out to be apparently a good compromise. And so this is the general form of what an attention-based message can look like. And as I said, the specific attention mechanism, if we have a multiplication here, or if we have a plus here or something else, this is all in principle up to discussion. The one thing that's not up to discussion is that the parameters that you have in your method, that they must not depend on the size of your input. Yeah? You want to be able to make predictions for sets of arbitrary size. Any other comments, questions? Yes? Okay, the question was, why is it harder to train this than to that? This one here is strictly more expressive. Yeah? So here, this can be an arbitrary function of both inputs, whereas this here this can be an arbitrary function, but it just produces a scalar, and this scalar is multiplied with a function only of xj. And here we have a function of xi and xj. Yeah, so this one comprises that one, but not vice versa. Okay, very good questions. So let's have a 15-minute break, and then we keep adding more indices here to reach multi-head attention.